is.
And yeah, you can. Thank you.
Okay, you should see now the slides. Am I right?
Yes.
Very good. Okay, so welcome. Thanks for the invitation. It's great to be here. Hope to see you in person at some point. So today we're going to take a look at some of our recent developments into basically the LLM and the large language model landscape with respect to graphs, especially the prompting part, the graph of thoughts, but also other methods for prompting and how they relate. So we all know the tremendous development in the generative AI in the last year. Basically, ChatGPT is as powerful these days as basically a lawyer. I mean, it could become your lawyer. But also a doctor, right? So you can actually use this thing to become a doctor because it just passed some medical licensing exams. And it also shows that it's actually, you might even prefer it to be your doctor because it's also quite empathetic and behaves really well. And also its development skills are, like software development skills are very, very high. So basically, yep, what is that for us humans? That's a bit of a different question. But really what we can see from some studies is that the difference between humans and other species was that we can actually build on top of each other's achievements and work in a group to achieve more. That basically means that we should now take these models and put them in a room, make them and let them make some society, but that's maybe a topic of a different story. Now let's take a look at how can we use these things for more powerful, more efficient computations that we are doing. For this, let's take a look at the overview of the processing pipeline for LLMs. So what we do there at the high level is that, as we all know, we take some raw data and we first conduct the process called pre-training, in which we obtain a pre-trained large language model. So that thing here, you can see the logo is a bit sketchy because that's still not what we actually want to achieve and obtain at the very end of the process. Because then in the second stage, we use something called supervised fine-tuning, in which we obtain a better version of this LLM called SFT LLM. And the supervised fine-tuning is basically conducted using both the human-based supervision and the data, right? So our humans are now taking active part in this training, this fine-tuning here. So this process provides the high-quality data and the high-quality supervision, but also it's quite expensive. And that's why what we do later is prepare another version of this LLM called fine-tuned LLM, and it's done in a couple of steps. So let's maybe move a little bit back. First, we are using human-based supervision and model-generated data to construct a so-called reward model. So by the way, there are other ways to do it. This is just one of these ways. Let's say the most flagship one a while ago is to create a reward model, the model that is going to be used later to automatize the process of the next fine-tuning stages, right? And once we have this reward model, we use it in an automated way to provide the supervision for generating the final version of the LLM that we call the fine-tuned LLM, I mean the final one that we can then interact with. So that's all what we basically do in the training process. And then what we have is the interaction with this LLM, right? So we can issue prompts, messages that we call prompts, and obtain replies that we call thoughts to actually use this trained model to do something useful, right? So, and now this can be done also in different ways, but also this has massively evolved in a couple of past months or a bit more than a month. So basically what happened is that what we can call the emergence of the generative AI ecosystem, where now this part is just a smaller part of a much bigger landscape that's emerging of how to integrate these models and their capabilities, especially the prompting capabilities, with other parts of the compute landscape. So what we can see basically is that on one hand, we have the part here, the upper part, which is the training related part, and the whole part at the bottom is the inference related part, right? So the prompting. And now we have especially been seeing a lot of developments into the prompting part. So on one hand, we can now give, there are also works about giving access to the different tools, scripts, and other things to the model and use it for better, more efficient, more effective prompting. There's also lots of works about how to psychologically enhance this process, how to make these models behave in a more expected way, but also how to use the psychological developments to actually make some problems solved more effectively. There's also there are also works about adding access to the web to the model. A lot of works about retrieval. So how do we actually now store additional data in separate stores, and then use this as a sort of long-term memory for making prompting cover much more information, again, as a human would do, right? So you also have your short-term memory, which is the context of the LLM, but also you have your long-term memory, and you need to usually spend a bit more effort to remember, to recall something from the past, but it's also very, very useful and much bigger in scope than a short one, and that's also what we've been seeing as attempts to be done in this landscape. And also something we'll be taking a look today, basically how to make this reasoning overall more structured and more effective by incorporating different types of graph-based structures and tree-based structures. So that's going to be our main focus today. We'll take a look, if we have time, at these other parts as well later on, but for now we focus on the prompting structures. So for this, let's take a look at a brief history of prompting paradigms. So at the very beginning, prompting was very simple. All what happened was basically that we had a scheme in which we gave the LLM the input, and we just obtained the output, right? So we are going to refer to this as the basic input-output prompting. And in this prompting, what we usually provide is some model input. So this is what we provide to the model in here. Let me just maybe quickly switch to the other pointer. So that's what we provide as our message to the model. We usually provide also so-called in-context examples, right? So we first, before we ask the actual question, we provide examples of the question and the expected answer, right? So here you can see that we have some simple mathematical tasks where we want to count some tennis balls. We provide the task and we provide the answer. And then we provide the actual question and we expect to get some answer, hopefully the correct one. Well, in that case, we don't really have a correct answer because this input-output prompting is not a very powerful way of doing these things. So what happened in January 2022 was the development of the paradigm called the chain of thoughts, right? So here, what we are doing, we are by appropriately structuring the prompt, we are forcing the model to explicitly reason in steps, right? So again, what we would do as humans, right, to solve a problem more efficiently. So here we have again the same question, but this time, instead of just giving in the context example the straightforward answer, we also kind of show the model how to do this reasoning, right? So we actually show, okay, look, we have this several steps because we started with that many balls, then we have to conduct some operations one by one, and finally this is the answer, right? And then actually the output is going to be correct, right? So by forcing this model in this to conduct this chain of reasoning in steps, we actually increase the chances for getting the correct answer by a lot. Then what happened was a realization that actually we don't even need to provide too many of these in-context examples, because in many of these cases, it's just enough to just instruct the model explicitly to proceed step by step, right? So, and the answer also is going to be mostly correct and more powerful in general, preserving these advantages of the chain of reasoning in the answers obtained. Around the same time, people realized that we may actually want to conduct some exploration into this landscape by exploring different chains of thoughts to hope that we can get a higher chance of getting the correct answer, right? And again, what we as humans would do, right? Because we also, when we try to solve a task, we also try to conduct and to try different paths of reasoning, and then usually select the one which comes with the best outcome, right? And the same was conducted here. So the scheme is called chain of thought with self-consistency. We'll just be referring to this as multiple chains of thought, because that's what it effectively does. You have some input question, and then instead of just having a single chain of reasoning with different steps of reasoning on the way, we do many of these chains, and then we select the one which comes with the best outcome. And then in May this year, there were two works that introduced the tree of thought independently, and there basically the key idea was to, at any possible step of this reasoning, so these of these multiple nodes here in the reasoning tree, in the reasoning chain, we can conduct this exploration at any of the steps, right? So instead of just at the input, we actually can do this generation of different next steps of the reasoning. So these steps can be, for example, some intermediate solutions or some other arbitrary, some other arbitrary steps in the reasoning. But important thing is that any of them we can now generate more steps from the same one, hoping to get some differences and to have some higher qualities in some of them, and then picking the best one to proceed further. But then the next step really should be, would be realized, would be graphical reasoning, right? And the motivation was, again, how humans think. Because when you now think about how we think, let's say that we have some goal to be achieved. So to achieve this goal, what we could do is, for example, come up with some idea, then maybe come up with some other better idea, then maybe combine these ideas to have an even better one, and then use this idea to create some plan of action, then execute this action, create some other idea based on the outcomes, and continue like this in a very use case specific way. So we are going to create some sort of action plan and continue with new ideas, new actions until we achieve our desired goal, right? And now the question is, do these structures on the right look like what we can see on the left? Well, not really, right? Because what we can see on the left is clearly a graph structure where we don't just have paths of reasoning, but we actually have more irregularity in the structure. We have some faults, we have some joins here, as we would say in the parallel programming language. So basically, this motivated us to create a graph of thoughts, to make these thoughts behave structure as a graph.
Would you call the diagram on the left as like a diagram for critical thinking? Like critical thinking on a subject?
You could call, I mean, so
what would you call it? Like what is the name for it? Yeah.
So I didn't intend it to be like a diagram for like in a very precise sense. I just created this to look like an average thinking that we would have, or at least as I would do, maybe as if also some other people I know that that would want to solve a problem. So it doesn't really have any resemblance to any formal work that's out there. But you could think of it as critical thinking. Yes, I mean, because you iterate, you revise your ideas, but you always keep track, okay, of what is the best in my. You critically think of what was the best in the previous attempts, in the previous actions, and then you always pick, the outcomes that you know that will enhance your current progress in a synergistic way, right? So in some sense, yes, you could refer to this as critical thinking. So the other inspiration was basically how the brain looks like. So there are three main or a couple of very fundamental ways that brain operates with, and one of these particular features is that the brain itself forms a very heavily interconnected network, and the others are that this network has very complex hierarchical clustered structures, but also lots of recurrence, right? So these two are basically the motivation to create a graph of thoughts in which we try to embrace these previous schemes and extend them in a principled way. So for this, we introduce so-called thought transformations. So these are basically ways in which we can transform our current intermediate solution through some simple units called simple unitary operations called thought transformations. So these can be, for example, operations called generate. So these are operations in which we, like in a tree of thought, we generate several next steps based on our current intermediate solution, current step of reasoning. The other class of operations are something we call enhance. So this could be, for example, here looping over a thought to refine it, to make it better. This could also maybe be seen as an example of a critical thinking, because you take your intermediate solution and you just apply some local operation over and over again until you achieve a desired outcome, or you may decide to just backtrack because this set of refinements, this sequence of refinements was just not very, very useful. But then also some other operations like here, where we conduct some arbitrary computation on a given solution to proceed to the next version of the solution. And then aggregation, right? So we also want to combine these thoughts arbitrarily so that we use synergy, right? So we take track of what was best in our current and past reasoning, and we use it at any stage to propel our future versions of the solution. So let's take a look at how this can be done for a very simple use case of sorting, right? So we could start with some sequence of numbers to be sorted. We could then split these numbers into subsequences, and this is what we would do in graph of thoughts with the generate set of thought transformations. Then we could apply some local local operation, basically do the sorting on each of these subsequences. This would be packaged and provided within the enhance operation. And then finally, we want to now take these aggregated these sorted subsequences and merge them, aggregate them into the final one. And this would be done in the aggregation call, right? And this is like a very, very simple example, of course. So we are sorting much larger sequences in our work. But the question, why sorting, right? It's so simple and it's almost trivial to be done, right? Well, on one hand, we start with sorting because sorting is a fundamental problem in the computer science. So we really want to start with it to see how now a new paradigm of computation deals with it. But on the other hand, really other approaches were also quite struggling with this. So it was very hard to make, for example, chain of thoughts or tree of thoughts to do the sorting for most of these cases correctly. And then again, as I mentioned, this is a very small example. So in reality, we have much bigger graphs because what you do, you don't just provide, for example, in this one particular case of sorting, you don't provide, let's say, one level of this splitting and then one level of aggregation, but you have multiple levels, potentially with different branching factors, and they form much more complex graphs with many levels and more complexity behind them. And then we also have more use cases. So some of these use cases are as follows. In one of them, we do keyword counting. So basically, as the input, you have a long, large document with some arbitrary text, and then you prompt the model to find, you want to find basically the occurrences, the numbers of occurrences of specific keywords coming from a given class. So what you can do, you can also split this into subdocuments of different granularities, count these things independently, and then merge them. And similar for NDA merging. So there's also the other use case, which was coming from our collaborators on how to basically merge documents more effectively and efficiently to distill the essence of these documents and still achieve a high level of accuracy and few hallucinations, right? So again, taking a set of documents to be combined and then splitting this into subsets, conducting the merging of them independently on these subsets of documents, and then merging them to achieve the final outcome. And again, these graphs are more complicated than these examples here.
Why the first step is called generate? Like, seems like kind of like.
Well, this is just our idea for basically this operation, and why we decided on this. I mean, because we sort of generate new steps here, right? So we can generate multiple of them. So these are all steps of reasoning. And now, I mean, in these examples, this is like splitting the. It's like splitting the input set into subsets, but then this is a very general operation because now these graphs can be used to model different types of reasoning. And for example, in other tasks, what is the case is that you can, for example, generate different multiple copies of the same, let's say that you have now this operation here that you want to do this local computation here, the merging locally. What you can do, you can also use generate to, for example, conduct multiple copies of the same output to have higher chances for getting a better one, right? So this generate can basically be done to do the exploration of the potential next steps with arbitrary branching factor, but also this means that this can be arbitrary next steps. So not necessarily only like splitting, but really anything else.
Okay, thank you.
Sure. So now let's take a look at how this things behaves in terms of its architecture and design. At the high level, what we have here is it's some interaction between the user and the controller of the graph of thoughts, right? So the controller is a sort of high-level module that is responsible for the overall LLM, like conducting the overall reasoning process towards solving a given task, right? So it's responsible for initiating, coordinating, and progressing the whole graph of thoughts execution. And now one important part there is the graph of operations. So it's basically a skeleton of the reasoning to be conducted, right? And this graph of operations can be pre-programmed statically by the user before the whole thing starts, because maybe the user has the better knowledge, but also it can also proceed automatically, driven on the fly by the LLM itself. And then the controller interacts with the LLM, of course. So it's done via two modules, the prompter module and the parser module, right? So controller will, like again, driven by how our structured graph of reasoning looks like, will issue requests to the LLM. And and these requests will be then replied with some thoughts that the parcel will take and build some state of these thoughts, right? So these icons are basically, they indicate the state of arbitrary intermediate solution to our task, and they form a graph reasoning state graph reasoning state. So basically, each of these nodes is some intermediate solution with its rank. So we have some fields here. So on one hand, there's a rank of this solution to always track where we are in our process, right? We never want to lose our ultimate goal of just solving a given task, right? So for this, we need to rank all these intermediate solutions of how good they are. And maybe we are nearly done, maybe we are still far away from it, to know better how to structure the future steps of reasoning. We also have the transformation, the information about the transformation that we used to achieve this given solution. We also, like in this state, we also keep the thought from the LLM and some other metadata. Right. And then we build this on the fly, driving our task solution until we arrive at the one with the rank which is high enough that we are just satisfied and we can finalize the whole process. And then we also have a reasonably large part dedicated to scoring and validation, right? Because we somehow need to score these thoughts and so that we know where we are in our task solving process. And this is actually on its own quite a complex thing in this field, because for simple tasks, like, I mean, simple in a way that, so there are some tasks that are very simple in how we can assess this quality, like sorting, right? I mean, we can just take the sequence and apply some heuristic to or based on our metric that objectively tells us how well a given sequence is sorted. We can just have some heuristic that quickly assesses it, or just like a script in Python. But then for other tasks, like for example, merging NDA documents, I mean, how would you score it, right? It's actually very hard to do this in an automated way. And for this, we have an option to fall back to either human or LLM feedback. So we
Yavaş.
Yes. Was there a question? No. Okay, then let's continue. So we also fall back to the LLM to score these intermediate solutions, right? And because it turns out that even if the LLM in its thought gives you something which is not of a very high quality, for example, you ask it to merge the documents into some new one, and you ask it to do it based on some criteria, and it does not really well, it will actually be able to say that, okay, this was not maybe a great attempt, right? So we use this capability to also provide this ranking in these more challenging tasks in terms of the ranking. And for this we also keep some data here to track these ranks also globally, to be able to quickly understand where we are in this process. And now all these most of these parts, I mean, the ones that are required for it, so are extensible, and we can basically take this thing and extend it with our API. Again, I mean, using some of this generate, enhance, and aggregate are just 3 of these thought transformations. We actually have a few others, a bit less relevant, but making it easier to build more effective graphs of thoughts. And also you can parameterize it, so you can basically parameterize it with different models. I mean, so we used ChatGPT and also played with Llama, but you can basically use any model, because it's all you need basically to do is to change the config files to point to a different version of the model. And it was already published at the next year AAAI, so you can try it online. The repository is there. Let's now take a look at some numbers. For the evaluation, we used the Swiss National Supercomputing Center, with really the main objective being to show that the graph of thought successfully harnesses the graph abstraction to enable more efficient queries. So we are going to see more of these plots. So in this slide, we are going to take a look at some sorting numbers. And in each of these plots on the x-axis, we compare different baselines. Right. So IO is the IO basic prompting. COT is chain of thoughts. TOT and TOT2 are 2 variants of tree of thoughts. I'll explain the difference in a second. And then GOT is graph of thoughts. Right, and then what I mean with these variants. So basically, we also explored a lot of these reasoning structures, right? So it was also the purpose to understand better how these structures enhance our reasoning, not just in terms of graph of thoughts, but really in general, right? And for this, in that particular plot, we vary the number of children, so like the branching factor at each of these exploration stages, and also the depth of this tree, right? So we also make these trees either so we usually fix the context size in a way that or like try to fix somehow the size of reasoning, and then we have some variation between the number of levels versus the branching factor. So the trees are, and also the graphs of thoughts are that we tried, but didn't really plot here, are either deeper but having a smaller branching factor, or a bit shorter but having like a wider branching factor. Right, and then here on the in each of these plots, on the left axis, you can see the accuracy of outcomes. So in that case, for sorting, it's the number of incorrectly sorted elements. So the lower, the better. And then the boxes correspond to this left side. And the right side is basically the cost of doing this whole reasoning until we solve a given task or fail miserably. And that's the cost in dollars. So again, the lower, the better, right? And then our bars correspond to the right side. So what we can see here is that on one hand, these basic schemes, the schemes that I refer to with basic are the schemes that don't really allow for this intermediate exploration, right? So this is IO and chain of thoughts, and they are actually, we can see, less powerful in their outcomes, less accurate in their outcomes than tree of thoughts, and especially than graph of thoughts. In terms of the costs, we can see that graph of thoughts is somewhat comparable to tree of thoughts. So it's sometimes, for some variants, it's a bit less expensive. For others, it's a bit more expensive. But overall, these three are more expensive than these basic ones. And that's really the trade-off, right? Because you want to make your reasoning more powerful. You need to invest a bit more resources into that because you may require to do this exploration at different stages to generate different variants and then pick the best one. So it all costs some numbers, right? So there are ways to try to decrease it, but let's not really speak too much about them, because now let's take a look at something more interesting. This is basically, you could be saying that, oh, but we are not really that much better than tree of thoughts because well, only just for some data points. Well, this was just for the smallest number of elements to be sorted. Now, if we increase the number of elements, we'll actually observe that the more elements we provide as the input, the better we are getting compared to other schemes. Right? So if we now sort more elements, we can see that especially IO prompting is basically not really being able to sort correctly in virtually none of the cases. Chain of thought is a bit better, but also not great. And then tree of thought is kind of also not becoming that great at this stage, right? And then we do have the best outcomes, and it's really, again, because we have this arbitrary ways of transforming the thoughts, right? So we don't just do, let's say, exploration at different stages of generating, but really are able to combine synergistically these outcomes at different stages to kind of use this thing that, okay, we split, we subsort, and then we merge at different granularities to propel the reasoning. And then we see this very similar pattern for other use cases. So we also tried intersecting sets of numbers. That's a very common kernel in different types of problems, like in graph mining. And here we have basically two input sets for each of these tasks, with some overlap of varying lengths, right? So again, we have the same type of plot. So we have again these plots for corresponding to different sizes of these sets that we are going to intersect, and we again see the very similar thing with both the costs and the accuracy, and similar outcomes for merging documents. Here we are sort of here we are comparable to tree of thought, but outperforming it in the costs, and all three things are better than the basic prompting outcomes, and then the basic prompting mechanisms. So that's it for how can we improve the prompting process with these structures. Now let's take a look at the initial attempt on why this thing actually works. So we have a very preliminary explanation that is going to be very hand-wavy, so I need to warn you. But we still try to some degree understand why we can see these effects. And this is just one. I mean, I'm not claiming this is going to really explain it, but it's just an attempt to understand in a more principled way how to compare these schemes and what may be going on underneath. Right. So for this, let's assume that we have something fixed. I mean, just to make the reasoning more structured, more principled. So we, on one hand, assume a fixed thought size. So each of these thoughts will have the same number of tokens. And also we assume a fixed context size. So we can also tell that in each case, we can only provide as many n thoughts within a context, and we can't really fit in more. And then while we fix these two things, we also define a certain new property for a given thought t. So this property is called volume of this thought. And the volume of this thought t is basically the number of preceding LLM thoughts that could have impacted t in some way. So the number of nodes in the structure of reasoning that are preceding t in such a way that they could have some impact on it, right? In this structure. So, and for this, let's now compare these schemes in terms of the volume, right? So intuitively, you want to make the volume as large as possible to maximize the potential scope of useful information that may have contributed to the quality of the final solution. And now for the chain of thought, it actually has a very large volume because, like, we have a single chain, we can fill the whole context with this chain now, right? And that means that the volume is going to be very large, basically equal to n. But at the same time, we also have many steps that we are going to refer in this slide as the latency, number of steps between the input and the output, right? And this large number of steps is also something not maybe very desirable because it kind of makes this reasoning potentially unnecessarily too long, and something useful may also be lost in the process, right? So so that's why this multiple chain of thoughts is getting a bit better, because now the trade-off, because depending on the branching factor k, we on one hand decrease the volume, which is not very good, because now we only can use effectively a part of this reasoning of this whole reasoning structure to get to the final outcome. But on the other hand, we also have lower latency. And then tree of thought brings it to the sort of extreme, because we now have even lower logarithmic latency, but also much lower volume. But then finally, assuming that we have some limit, that we take some limit in the structure, so we have, for example, the fully balanced binary or k-array tree in general, and the same for graph of thoughts. If we have the limit structure of splitting and aggregation here, we can also see that in the limit, graph of thoughts will come with the basically volume equal to that of the chain of thought, but also very low latency, because we might be able not to lose any thought in the process, because we may always try to somewhat combine them at some stage to provide to use the synergy to proceed.
How about in terms of storage efficiency? Like if you compare them, like memory efficiency, storage efficiency, are there differences between them?
I mean, so what you are asking basically can be answered on two different, I would say, in two different levels. So on one hand, memory efficiency understood as what we need to keep track of all that reasoning on, let's say, our user side, because we need now to track all these things. So this is one aspect of memory efficiency, and yes, we need more storage for that. That's a very good point. But the storage is really negligible, because these graphs don't have billions, of vertices. So they have much less.
I was asking in terms of the queries like made by the user. So that will take more time, I guess. Is it like evaluating those queries, like because you have more? I mean, like the ones on the left. I might be wrong, but the first one, second one, third one are more hierarchical structures. But the one that you're suggesting is not very hierarchical, like so that you have. You can evaluate the things in a better way. Is that a correct?
I would agree. I would disagree, because we are also hierarchical, right? In a way, I mean, what you can do with, it's you could basically think of this as tree of thoughts plus new operations like aggregation, right? And you could also apply hierarchies here. And now I would say that in terms of the time,
no, but that's the benefit of
right?
Isn't that the benefit of suggesting the graph on the right? Your graph of thoughts is like it doesn't necessarily have to be hierarchical, I guess. Or are
it doesn't have to, doesn't it? But that's the power, right? You can actually make it more flexible.
That's the power of
to fit in different use cases, right?
Right.
But now the point is that because in each of these schemes you can make them very protracted, very lengthy. Like with tree of thoughts, you could also now generate decide on having a very deep tree with a lot of exploration at every step, which will result in many intermediate solutions. You could also now have a chain of thought with many different stages, right? So that, I mean, that really depends on you. And in the graph of thoughts, yes, it might take some time, because now you may want to think, okay, I need to split this, and then it's going to be aggregated. But I wouldn't say it's going to be longer in that respect, that you now need to do it as the user. And in terms of memory efficiency, so it's really negligible, because I mean, until we have a stage where these where this reasoning takes a lot of space, then I mean we are safe, because I mean we can process graphs like in data analytics, we process graphs with billions of vertices, right? So that's not really a problem. And this graph doesn't really, I mean, yes, we need we also have some bookkeeping of the past thoughts, but again, this is something you can also decide not on doing, right? So it's really how you build it in the framework.
Okay, thank you.
Sure. So yes, we have our prompting structures. So maybe if you want to, because I then have a very bit of other, like a small amount of some other research threads we are seeing in the other parts. But if you want to have maybe some discussion about prompting itself or some questions, you can maybe go ahead now.
A question about, can you hear me?
Yes, I can hear you very well.
So you had a prompting API you showed in the back of maybe slides 14, I don't remember. You showed you have an API for prompting. So how can you use this, or is it possible to use it for because the examples you gave about sorting, document merging, or
You mean this one, right?
Yeah, numbers. Maybe here. So how is it easy to use or extensible, this prompting API? If we want to do this for, let's say, more complex text tasks, I'm not saying that counting numbers or intersecting sets are not
Sure.
but they are not practical use of it, right? I mean,
yeah, of course. But again, as I mentioned, right? So we already use this for a bit more complex things like merging documents, which you actually have to provide some documents and with some contents, and then you have to merge them. So I mean, you do this. You basically can do anything that you are able to fit in this kind of structured prompting, very general structure. And how you do it is on a couple of levels. So on one hand, what you can extend is basically the operations themselves, right? So you may now want to provide other operations. The other thing that you can extend is basically,
and other operations will be in the graph operations API.
Yes, the graph operations. You can basically try to come up with new ways to transform the graph. On the other hand, it's also like really the core of how you change the use cases themselves is basically prompter and parser and validation. So you kind of pre-program the contents of the prompts for these different operations. We provide the skeleton, and you basically extend some routines and extend them by providing some contents to in terms of what has to be done by the LLM, and then how to process the outcomes from the LLM for what you ask it to do, and also how to score that, right? So for example, for document merging, this would be providing some way to inject document contents into the prompt, provide some text that tells the LLM, okay, now I want you to merge, several documents into one, specifying the number. So this is going to be again parameterized by the graph of thoughts, but you may also want to kind of fix it. And then for the score, right? I mean, what to do with the score and how to score it basically. So these are kind of this general ways of parameterizing it and making it specific to a given use case. And I mean, as I say, we have this done for both these very simple things, but also for these a bit more complex things that you may want to do with documents, like this keyword counting. So this is another thing that you do with documents. You parse a document and want to count some keywords coming from a given class. Like let's say you have a document, you want to get names from it and how many of these names were mentioned. So we have these examples online. You can check them how this is done specifically, and then you can just use it as template to extend it towards yours.
Okay, thank you.
Yeah.
I have a question as well.
Mm-hmm.
First, thank you very much for the talk. I was just wondering what the metadata is in this context. So in the bottom right side, we mentioned a metadata. What precisely is it?
I mean, so this can be anything that it's also something you can kind of parameterize yourself, right? So and provide yourself depending on the use case again, right? So this can be, for example, maybe the branching factors from previous operations and how many of them there were. So it's very something much arbitrary that I would say depends on the use case.
Okay, thank you.
Yep. So Any other questions? No, so maybe I will also mention very briefly other threads we have in other parts. So for retrieval, we have ongoing works about basically how to scalably access and fetch and manage data in graph databases also for the future purpose of making this prompting process better. So we have a couple of works published here. On one hand, we have a work about neural graph databases. So basically how to combine, because now we would like to store different chunks of information that we have in our reasoning process, but also other types of information, because it's a general mechanism that we have here in a graph database in a scalable way. Right? So on one hand, we have a work about how to make graph databases combined with neural capabilities to, for example, build embeddings faster and in a more effective way for some given task that we have in mind. And the other thread of works is something we call the GDI standard, which is basically done in a very deep analogy with MPI. Is basically a standard that prescribes building blocks for building for constructing scalable graph databases that have a couple of other cool properties. So this is something we just published at SC, and it's basically a way to build graph databases that are on one hand easy to deal with. So they are programmable, they are portable across different classes of devices, they support different major workloads like online or analytics or transactional workloads, but also powerful in how they solve these workloads. So they come with high performance, high scale, and support arbitrarily big, large data sets. And just maybe a very few slides about this GDI. So the key idea in GDI is basically stemming from our observations of the field and the field of graph databases and some issues that are in this field. So on one hand, most of these systems are not really able to process reasonably large scales. So just to make it more concrete, the largest scale published so far before GDI for graph databases was in the Microsoft A1 graph database, where they scaled their execution to nearly 3,000 cores and 245 compute nodes. And the other concrete example illustrating the challenges in the design of these systems is a comment that we found in the production repository of one of the systems we are analyzing. So we did a lot of comparisons and investigations into the design of these systems, and basically we found in the code that look, we don't really know the effects of running this OLAP query, which stands for online analytics, when running concurrently with OLTP, which stands for online transactional processing. So don't really use it in production, right? So this was kind of the motivation to in a systematic, principled way, understand how to deal with these challenges, but also with these other challenges like portability and performance. And this is what brought GDI to daylight. The key idea there was basically to bring the best practices of the message passing interface and its fundamental design feature into the landscape of graph databases, where the design feature that we refer to is basically breaking down the complexity of a system with the separation between the hardware agnostic interface, our API that contains the building blocks for the portable building blocks, and the hardware specific implementation. Right. So in the context of these graph databases, basically what we have in MPI is that we have the separation between the MPI standard and the MPI implementation, right? That sits directly on top of the hardware access layer, which is vendor specific. And then this MPI standard enables us to, as we know for many decades, enables us to basically provide provides fundamental performance critical building blocks that we can use for communication in a parallel environment. And then on the other hand, we have also, thanks to it, a portable and productive API that we can use for developing scalable parallel applications, right? And now because these two, the first, the upper layer, the standard is hardware agnostic, and the MPI implementation is hardware specific, we can much easier provide, design and implement HPC application of our choice, rather than dealing with the hardware layer on its own directly in a monolithic design, right? And also portable thanks to this separation. And basically this was the key idea for GDI, to have a GDI standard, which is hardware agnostic, and GDI implementation underneath, with the standard providing the specification for fundamental performance critical building blocks for graph data layout and graph transactions in a parallel setting. And it provides a portable and productive API for building these graph databases in a much easier way than before. So we can also use GDI, it's online, and maybe some example number of what we can basically do here is here on the x-axis. So this is like the plot for, basically it's like the plot comparing a graph database based on the GDI. So we refer to this as GDA because it stands for GDI RMA. So it's like implementing GDI standard for RDMA classes of systems. And on the x-axis, we can see the number of servers. So we scale from 1 up to more than 7,000, which is the full scale of the Pisdane supercomputer. We also do the weak scaling here. So we scale graphs that we generate from around 134 million vertices to 275 billion. So these graphs are maybe not extremely large because there are graphs that were processed in the community that were larger, but these graphs are graph database labeled property graphs. So they don't just come with the structure like edges and vertices, but they also come with a very rich additional data, labels and properties in different configurations attached to vertices and edges, right? And on the y-axis, we have the runtime to conduct BFS. So here we compare to, so on one hand, what we can see is that we successfully scale to this full scale of Pisdane, and that's really more than 120,000 compute cores, and it's the largest run ever for this class of workloads in the whole literature, improving on the past by 26x versus the biggest scale published by Tiger Graph for that class of queries, and 950x for Neo4j versus Neo4j. And now there's something interesting. We also, thanks to the fact that we programmed this for RDMA using one-sided communication, again, details are in the paper. We can see that we compare to Graph 500, which is like a hand-tuned implementation of BFS. And of course, we expect us to be slower because BFS is a hand-tuned implementation for BFS that doesn't really support any graph modifications or transactions and other classes of workloads, right? And we do all these things. So we're expecting to be slower, but we're surprised to see that we are basically only around 3 to 5 times slower for smaller scales, and then for the larger scales that we are able to try, we actually even outperform it at some point by some certain margin. So we have more results for that part. Also for transactional queries, we have the same scale, big scale of results, and again, things you can check online. And now we are working basically, okay, how do we use these graph databases together with the structured prompting to make basically prompting also more effective, more powerful. So any questions regarding this part, maybe?
Any questions? Yeah. Well, we read the paper, a C paper, and we discussed in our group. So I suppose is there any question about the SC paper, the GDI? No. Very, very good work.
Thank you. So I think we are going to be done, right? Because we have like 3 minutes left. So yes.
Do we have any final questions to Maciej? Questions?
It was a very nice presentation. I learned a lot. Thank you very much, Maciej.
Thanks.
It was very good.
Thank you.
I guess that's it. Do you guys?
One small question, like in the early prompting structures earlier, and do you have any plans to sparsify that chain of thought? Not chain, but like the graph of
That's
thought,
a very good question.
Yeah, do you have any plans for that one?
I don't think we need it at this point, honestly. I mean, these graphs of these structures of reasoning are not really that large at this stage that we need sparsification, unless we want to use sparsification for, to distill more essence of the reasoning. But I don't think they are. I mean, okay, actually, yeah, this is actually not a no. This is actually potentially useful because we can actually use sparsification now to make costs much lower, maybe in some way. But I would say it's actually a very hard topic because it's really. Like you don't really build these structures statically before. I mean, you ideally want these structures to unfold as you go, right? So how would you sparsify the unfolding structure. I mean, you can't. I mean, what you should probably do is what I think could be and is going to be done is kind of implicit sparsification by having a better sampling scheme for the exploration, right? You will be able to generate these sub-solutions or these next step solutions or general next steps in a more effective way, requiring much less attempts, like basically making the branching factor much smaller and thus reducing the cost. So this is what I would maybe refer to as some sort of selective sparsification. It's more like like making this sampling and this generation more effective. But this could be seen also like I mean like on the same level as sparsification, right? So but for the purpose of decreasing the costs of inference.
All right. Thanks.
Thank you. Thank you very much, Maciej. When the video is out, so I guess we will let him know.
Maybe tomorrow.
Tomorrow,
After that,
probably?
yeah.
Okay. In a couple of days, it will be out.
Sure.
Okay.
If you
Thank
need
you very
help with
much.
anything, let me know.
Okay.